So welcome to another video uh, on operational amplifiers. So today we'll be talking about the types of operational amplifiers, and the type of an operational amplifier depends on the intended purpose of the operational amplifier. So if we have a design operational amplifier, we want to use it to perform addition, we call it a summer or summing operational amplifier. Then you design one to differentiate an input signal. We refer it as a differentiator. We have integrator, then non-inverting differential as well. So when it comes to the inverting operational amplifier, for example, out of that, you can get a differentiator, integrator, and summing operational amplifier. Then we also have another operational amplifier, which is regarded as a non-inverting operational amplifier. So you can use this to amplify a signal, and then you can modify in a way to get another operational amplifier referred to as voltage follower. And we have differential operational amplifier as well. You want to find the difference between two signals, let's say V1 and V2. Then we can do that using a differential operational amplifier, and it can also be modified in a way to get what we refer to as a subtractor. Now let's start with an inverting operational amplifier. And when it comes to an inverting operational amplifier, we first start with the operational amplifier. All right, as you can see here, the operational amplifier here is having, like always, two input terminals, and then we have one output terminal. So the two input terminal, we have the inverting input, which is the negative terminal here, and then so we have the inverting, which is the negative terminal, and the non-inverting input is the positive terminal that we have, and then we have the output terminal as well. Now, in that case, for an inverting operating amplifier, we make sure that we connect an input voltage into the inverting terminal, right? So in designing an inverting operating amplifier, meaning we are going to be connecting the voltage inputs into the inverting terminal, and then before it goes into the inverting input terminal, we connect it passes through a resistor, which we label here as the input resistor, that is Rin. And from there, we can feed back the output signal that we get out of the operational amplifier back into the operational amplifier through a feedback resistor labeled here as RF. And with this, we make sure that the non-inverting input is grounded. So we connect it to the ground, and that means the voltage which at that input terminal is going to be 0. And based on this, we know that an operational amplifier is going to have a very large gain, meaning it has an infinite open loop voltage gain. And in order to get that large gain or open loop voltage gain, that means the differential input has to be what? 0, right? And you get 0 because V2 will be equals to V1. So if V1 here, meaning you ground the non-inverting input, right? That means what? V2 will be equals to V1 because the differential input there, since it's having a very large gain, will be 0. So we have V2 being equals to V1, and this is going to what? 0 as well. So we refer to this as virtual ground, meaning grounding the non-inverting input terminal, which is going to make it 0. That also makes sure that V1 is also 0 as well. And in doing so, we can have a situation now whereby we can locate a node here, right? Or a junction whereby there's what? Interconnection of what? 3 terminals. We have a connection of 3 terminals here. So we can label here as node A. And at node A, you can see that we have current entering the inverting terminal. And since, again, an operational amplifier is having an infinite open loop, infinite input impedance or resistance, meaning the currents into the operation amplifier is almost zero. So we get IR, which is the current entering the input terminal, is going to be zero. And here at node A2, you can see IN is entering node A, and then you have IF leaving node A. So in that process, we can apply Kirchhoff's current law at node A. So you can see IN is entering, and IF and II are leaving that node. So you get the equation to be IN will be equals to the sum of what II, which is the current into the operational amplifier, and then the feedback current. Since I is going to be equal to zero because we are dealing with the operational amplifier with an infinite resistance, input resistance. So we get IA to be zero, and then IN equals to as IF. Right. Then from here, bear in mind to VA, which is the voltage at node A, also is going to be equal to a V2 because right, VA here is connected to what? This the inverting input, right? And the voltage at that input is V2, which is equals to V1, and which is also equals to zero as well. Then we can now apply our knowledge of applied electricity to find the output voltage, because we want to make sure we get a relation between the output voltage and the input voltage that we have, which is V here. And in doing so, we come to a node A. If we are at node A, we know that I is entering node A, and I can get the potential difference between what V in and that of what voltage at node A. Then in that potential difference, we look at where the current is coming from. You can see the current is coming from V in. So V in here is a higher voltage or potential, and the current is going to arrive as well at node A. So the voltage of node A becomes the lower potential. So we have the difference potential, or the potential difference is going to be equal to V in minus VA all over Rin, which is going to be the resistor that is between the two voltages. Then this will equals now IF. And now when I get IF, IF is also we get it through what? The potential difference idea, which is that again we are at node A. This side IF is what leaving the load. So the feedback current is originating from what? Node A. So node A here is a higher potential. Then from there arrives at what the output voltage VO. Right? So VO here is a lower potential. So we get VA minus VO over again the resistor, which is between the both voltages, and now we want RF. So we have VA minus VO over RF. So we make the output voltage the circuit. So we get minus RF over Rin times Vn. This is the formula for inverting operation amplifier, and all the other inverters that we're talking about. For each of them, we always try and get the relation between the output voltage and then the input voltage. And this is very important because we want to see how the operation amplifier is going to react if we have an input into that very operational amplifier. So we want to get the output voltage in that regard. And we also have another gain, voltage gain, which we refer to as closed loop gain. And when it comes to closed loop gain, just like any closed loop gain at all, is the general formula is that you take the output signal over the input source signal. Output signal over the input source signal. So if we are abiding by that rule, you can see that the output signal here is the VO, which is the output voltage here. And when it comes to the source signal, that is going to V in. So we have V over V in. So we can go back to this formula and then make V over V in the circuit. That will just be our closed loop voltage gain, and that will be equals to minus RF over RA. So this is how we are able to calculate the open loop voltage. We are able to calculate the output voltage when it comes to an inverter operation amplifier as well as closed loop voltage gain. And see you in the next video. Bye bye.